Let's look at how entropy changes when a reaction occurs and how that affects the spontaneity of the reaction. So we'll start by looking at a specific reaction. Let's take a mole of hydrogen gas and half of a mole of oxygen gas and combine it to form water in liquid form. And let's imagine that we're going to do this at 25 degrees C. Okay, so first of all, let's predict what delta S should be for this reaction. So let's predict the sign. So you often be asked to predict whether a reaction would have a positive or negative delta S. So you're looking at the entropies of the products and the reactants. And you can do a pretty good job of this as long as there's a change in the number of moles of gas. So if we look at this, we can see on the left-hand side we've got 1.5 moles of gas. On the right-hand side we've got 0 moles of gas. And the entropies of gases are much higher than other phases because the density of states, in other words, the spacing of the quantum levels, are so close together that the value of W, which determines, of course, the size of entropy, is so large. And so because of that, we could predict confidently that this is going to have a delta S that's negative. So we're going to say delta S for this reaction we think is going to be a negative number. That's our prediction. All right, now we can actually calculate the delta S of this reaction really easily. You know that all substances have an entropy of 0 at 0 Kelvin, and that as we increase the temperature, the entropy increases. And we can measure how much that entropy increases as long as we know the heat capacity of the substances. So if we do this, we can calculate the entropy at 25 degrees C. So these absolute values for entropies are tabulated in tables in the back of your textbook. You can also find them in the NIST webbook. So we can look these things up. So since we have the entropies for the products and reactants, we can calculate delta S for this reaction. So let's do that on the next page. So if we want to calculate delta S for a reaction, we just take the entropy of the products minus the entropy of the reactants, and of course we take into account the stoichiometric coefficient. So it's just like calculating delta H. So we need the entropy of water, and physical states matter, so let's keep track of that. We subtract the entropy of the hydrogen gas, and we subtract 1/2 of the molar entropy of the oxygen gas. Okay, actually I didn't put my physical states in there. Let's put those in here that we're talking about gas. Okay, so we look these up, and as I said, you can look these up in the back of your textbook or on the NIST chemistry web book. And usually you'll see these denoted with a little circle meaning standard, and that just means that we're looking these things up. They're pure substances and they're at 1 bar of pressure, basically 1 atmosphere. So let's get those numbers. So the entropy of pure water, liquid water, is 70 joules per mole per Kelvin. The entropy of hydrogen gas is going to be 131 joules per mole per Kelvin. And we've got the entropy of the oxygen gas, which is 205. Okay. Incidentally, you'll notice some trends here. These are both diatomic gases, but this one has atoms that are a little bit heavier, or quite a bit heavier than hydrogen, and in general that's going to lead to higher entropy. So that's another trend that you might notice when you're looking at third law entropies. The more complex and the heavier the molecule in the gas phase, the higher the entropy. Okay. So let's go ahead and get the result from all this. The overall delta S for the reaction is a negative 164 joules per mole per Kelvin. You'll notice we predicted that delta S for this reaction would be a negative number, and indeed it is, negative 164. This definitely prompts the question, is this reaction possible? It's a very common misconception that all processes that are possible have a positive delta S. The entropy for the system always increases. But that's not true. What we care about is the overall entropy of the universe. So the overall entropy of the universe has to increase, and we could write this like this. We could say delta S for the universe, which is equal to delta S for the system of interest, which in this case was our reactions and products, plus the surroundings. That's everything surrounding your reaction. That sum has to be greater than or equal to 0. We can't have a negative change in entropy for the universe, but these individual pieces could be positive or negative. It's just the sum that has to be positive. So we already saw that for this particular reaction, the system of interest had a negative entropy change. Now that implies that this has to be positive, and it has to be at least as big as 164, probably much bigger. So this should be a positive number. Let's find out what this number is. Now, why were the surroundings affected when we did this reaction? Well, if you've ever seen a demo of a hydrogen balloon being blown up, which is what this is, hydrogen burning in oxygen, you know that one product of this is a whole lot of heat that's released into the surroundings. And that heat being released into the surroundings is going to increase the entropy of the surroundings. So we're going to increase the entropy of the surroundings. Let's figure out if we can quantify that, put a number on it, and see how big this delta S for the universe is. So we'll do that on the next page. So delta S for the surroundings, I'll just abbreviate surround, is equal to Q surroundings divided by the temperature. All right, great. Well, what's Q surroundings? Well, if you think about it, the surroundings are in thermal contact with the system. So if the system gave off heat, that heat had to go into the surroundings. There's nowhere else for it to go. So this must be opposite in sign to Q for the system, right? Because if one thing gives up heat, the other thing gets it. So they have to be equal and opposite. So that is going to be negative delta H for the reaction. Okay, let's go back and see what reaction we're dealing with. You might notice that this reaction is the heat of formation reaction for water. We're making water from its elements. So we can just look this up. So we can see the heat of the reaction, when we look it up in a reference table, is equal to a negative 286 kilojoules per mole. So that's the heat of reaction for the system. So for the surroundings, we're going to change the sign on that. So for the surroundings, instead of it losing heat, it's gaining heat. And we're going to go ahead and convert that to joules from kilojoules. And we said we were running this at 25 degrees C, but of course we had better convert that to Kelvin. Always do that with your entropy calculations. Remember, we're still calculating delta S of the surroundings. Okay, so we've got this divided by that, and that comes up to a positive 960 joules per mole per Kelvin for delta S for the surroundings. And remember, for the system, we got that the entropy change was a negative 164. So we've got negative 164, a positive 960. We can see that overall this is definitely going to increase the entropy of the universe. Let's just see how much that is. The delta S for the universe for this process. So we said it's delta S for the system plus delta S for the surroundings. So that was a negative 164 joules per mole per Kelvin, a positive 960 joules per mole per Kelvin. And we can see that that equals 796 joules per mole per Kelvin. So definitely a positive number. And so we can say the entropy of the universe increases when we burn hydrogen and oxygen to form water. Not because the water has higher entropy, but because it gives off so much heat that it increases the entropy of the surroundings. So whenever we're using entropy as a criteria for what's going to be spontaneous in the universe, we want to use the total entropy, the entropy change of the universe.